Geology is affected by different structures that is producing displacement of movement that you must to take account, no? When you are making an image of the geology in your mind. But it's really complicated. It's not easily. When you can 2 or 3 weeks spending in the field, it's complicated. It's complicated. You need more time just trying to understand, and you must to change your mind.
None of our projects, the geology is obvious. In fact, I've been to hundreds, if not thousands, of mineral exploration and mining projects around the world. And I've never seen in the case of both our projects, geology as complicated as we've got, where the genesis of these projects has been so complicated. If I take the Santa Maria alluvial, that is a complicated story, and it took us best part of 18 months to figure out exactly what was going on. At Oropesa La Grana, I'll leave La Grana aside because La Grana is a typical tin deposit. You find lots of these around the world. We're going to have another look at it, and maybe we'll find something there which we can mine, and it'll be a good grade if we do. But coming to Oropesa, from a geological point of view, there are no clues whatsoever around here that there should be any tin. There's nothing at all which indicates tin. There's no granite here, there's no known alluvials here, there's no nothing. There's no indication of tin. So we had a look at all the material that was produced by the Spanish Geological Survey, and we agreed with them that there was one structure dipping to the south. And as it turns out, this was not correct. When we first started looking at Oropesa, we thought it was conventional geology. Unfortunately, that didn't turn out to be the case. I guess it's pretty good news, because otherwise, if it had been conventional geology, somebody else would have figured it out before. I guess it's kind of like going into a battle. The first encounter with the enemy destroys all the plans, and you have to go and plan something new. I guess that's one way of looking at it. As you drill, that's really the only real way to test what you've got. You find that some of your assumptions are incorrect. That's pretty much a given. In the case of Oropesa, we were looking for conventional geology. We didn't get conventional geology. We have deposits which are much thicker than normal, and we have deposits which dip at a much lower angle than normal. And we have to fit our models to understand why that happens. And there are 2 possible theories which fit that. Originally, we thought we were in a graben structure, and the graben structure does make logical sense, but it doesn't with the angle of dip, which we see the mineralization in. And that's what started moving us away from the graben structure theory, and made us have a look at some of the boreholes which went through the fault which acts as the northern boundary of the favourable horizon of conglomerates and quartzites. Now, there's only really 2 explanations which can fit an angle of dip of 40 degrees unless there's been massive folding, which we don't think has happened. One is called the listric fault system. People may know some of the gold deposits in the western US. It's often known as basin and range geology, and you get listric fault systems there, and some of the world's biggest gold deposits are associated with listric faults. What this is a low angle fault, like this, and this bit has moved down, and so basically this piece of ground here has slid down along here. Now, in our case, in Oropesa, the theory is that there would be a granite over here, maybe 2, 3, 5 kilometers away. It's difficult to know. And the mineralization would have found this fault, and we call this a detachment fault. It's normal faults, that means it's a pull apart, so it's relatively open, and the mineralization flows up this way. Now, in a listric fault system, you get these splays coming off like this, the low angle, and the mineralization comes up along these. These have been opened up, and so mineralization flows up these faults. If we take a close-up of, say, this area here, we find here's your detachment fault, this bit's slipping down, and you have the splay coming off like that, and here you would have splays coming off again, and sometimes you'd have things coming up like that. So these are the bits which should be mineralized.
and maybe this would be mineralized as well. This is generally only weakly mineralized, so this would be your target. So if you drill a hole coming down like that, sometimes you'll go through 1, 2, maybe 3 zones, sometimes you go through one weakly developed zone. Now this is a possibility. However, there is another alternative. And this is one of the reasons why we're drilling on a comprehensive grid. We're putting in a grid of 50 holes to determine what the structure is. This is so important because we're looking at a system which appears to be a very large tin system. And by the time we've finished our 50-hole grid and we have the results assayed, we'll know which model we're looking at. So now here comes the third possibility. This is called a fault couple or a shear couple system, and it's not the easiest of things to understand. Now we're now looking at a plan or a map, so we're looking top down. So what you have at Oropesa is you have 2 fault structures, which is, because there are 2 of them, we call them a couple. These faults will have had horizontal and also vertical movement on them. We don't know how much the movement is yet. And what you find in between, you find sinestral or dextral mineralization, shaped kind of like that. Thinnest near the individual faults and thickest in the middle. And what has happened is the ground has been wrenched. I can try and illustrate it with a book. And you'll find that when you apply the pressure, you get openings like this, and it's those sort of structures into which the mineralization flows. Well, we don't just have one of these things, we have a series of them, one after the other, all the way along approximately 1,300 meters. I don't know how many of these things there are, but there appear to be quite a lot of them. Where we have drilled them, we can see the vertical difference between them, and I'll now draw this in sections, so we're now looking into the paper. We see this type of structure developing. So you'd have your fault here, let's say that fault, and you'd have your fault here. So this part will be mineralized. It won't be totally mineralized. There'll be gaps in it, like maybe that bit won't be mineralized. And you have a structure shaped like that. In the middle it opens up to maybe 30-40 meters thickness, and on the edges it's maybe 5 or 10 meters. But we find they're stacked up, one on top of the other. Now some will be better developed than others, and some will be less well developed. And we find, from what we've seen so far, the distance between these things is about 50 to 150 meters. It varies. And so we think we have these things stacked up one after another. And as you go along here, you'll find these things stacked up going this way. So if you drill through these deposits, you'll find you go through a reasonable thickness and another one here. As I said, these aren't totally continuously mineralized. You get breaks in them where the mineralization doesn't happen. So that might be barren, those little bits there might be barren. But we get these things repeated one after another. This is what it looks like. I've not come across this type of structure in tin anywhere before, but there are quite a few mineral deposits in the world where you see this.